Good day and welcome to our lesson on electrical formulae. Let's start by looking at the difference between voltage, current and resistance. Well, here as we can see by this meme, you can think of voltage as that driving force that pushes electrons through a conductor. Current is the amount of electrons that actually pass through the conductor. And resistance, as the name implies, is what is trying to stop those electrons from flowing. Let's get a little more technical with current though. We say that electrical charge is the physical property of matter that causes it to experience a force when placed in an electromagnetic field. The unit of charge is the coulomb, abbreviated as C. An electric current is the rate of flow of electric charge. It is how many electrons pass through in a certain amount of time. Hence, we can have our first formula, I is equal to Q over T, where I is the symbol we use for current, Q is the symbol we use for charge, and T is time. So let's look at an example now. Let's say the makers of a popular cell phone have upgraded its battery capacity from 3,600 coulombs to 5,400 coulombs. The standard charger can deliver a current of 1.2 amperes. 1. What is the time taken to charge a phone using the old battery? 2. What will be the time taken to charge a phone using the new battery? And 3. How much more time will it take to charge the new battery than the old battery? Also, in order to maintain a competitive edge, the cell phone maker needs to keep the same charging time for the new model as the old model. What must be the current rating on the new charger to accomplish this? So let's see our solution. We begin by identifying our givens. The Q, which is the charge, is 3,600 coulombs and the current is 1.2 amperes as advertised on the charger. Rearranging our formula, we get T is equal to Q over I. Substituting, we will then calculate the time to be 3,000 seconds, or in other words, 50 minutes. Part 2 is pretty much the same, but we instead get 4,500 seconds, which is 75 minutes. Part 3 is simply to find the difference between these two values. So that will give us 1,500 seconds or 25 minutes. So an advantage of the new battery is it can take a bigger charge and hence last longer. But also the disadvantage is it takes longer to charge. Part 4. We know we want to charge it in the same amount of time but given the new capacity of battery. So the new charging capacity is 5,400 coulombs. The old charging time is 3,000 seconds. What current rating should we have? So we have I is equal to Q over T. Substituting, we get 1.8 amperes. And that should make sense to us because if we want to charge more but within the same time, then you have to put in more every second. And that's what the current is. How much charge is going in every second. Next, we come to voltage. Potential difference, abbreviated PD, also known as voltage, is defined as electric potential energy per unit charge, and it is measured in joules per coulomb, or for short, just volts. What is meant by electric potential energy per unit charge? It means how much energy is put into every little electron. So based on that formal definition, we get our formula. V is equal to E over Q. Let's look at an example now. Let's say a battery circulates 200 coulombs of charge around the circuit. If the potential difference across a lamp in the circuit is 24 volts, how much energy is converted into heat and light by the lamp? So our solution is as follows. We identify our givens, Q is 200 coulombs, V is 24 volts. We substitute, multiply, and we get our answer of 4,800 joules. Too easy. Let's proceed to power. So electrical power is the rate at which electrical energy is transferred by an electric circuit. So based on that, power is energy divided by time. That's an old formula, but we can make a new one for electricity. Let's see. We know that V is equal to E over Q. So rearranging that, we have that E is equal to QV. Substituting that in place of E, we get QV over T. We can separate the QV over T into Q over T times V. But Q over T should look familiar. That's one of our formulae that we just learned. In fact, it's the very first formulae that we learned. So Q over T is current. So that brings us to P equals IV. Power is equal to current multiplied by voltage. Let's look at an example. The stereo set in Mr. Castillo's home is rated at a power of 230 watts. Calculate the current that will flow through Mr. Castillo's stereo set when it is connected to the 110 volt main supply. So let's see, should not be too difficult. We identify our givens. P is 230 watts, V is 110 volts. Rearranging, we get I is equal to P over V. Substituting, we get 2.09 amperes. Please note, however, that this is on the maximum setting. If that radio was on full blast, only then will it be using 230 watts, and only then will it be using 2.09 amperes. If it is on half setting, then it will be using half as much. Now we come to calculating energy usage. So the total energy in kilowatt hours is the power in kilowatts multiplied by the time in hours. Remember that since power is energy divided by time, then energy is power multiplied by time. So if we multiply power in kilowatts multiplied by the time in hours, we get the unit of kilowatt hours. And it is commonly used as a billing unit for energy delivered to consumers by electric companies. For a more detailed explanation, let's take a look at this clip.
A watt is a common unit of measure for electrical power. So if a watt is a measure of electrical power, what exactly is power? Power is a measure of the instantaneous electricity being used when you turn on any electrical appliance. You see power requirements called out in watts on labeling for everything, from light bulbs to microwaves. Kilo means 1,000, so a kilowatt is 1,000 watts. However, both watts and kilowatts are only a snapshot of instantaneous electrical usage. Energy, which is what we really care about and what the utility company charges you for, is that accumulated amount of power being used over some period of time. Energy is expressed in kilowatt hours.
So let's take a look at this example now. In Mr. Castillo's home, once again, the stereo is rated at 230 watts and the electric griddle is rated at 1500 watts. The stereo is used for 3 hours and the electric griddle is used for 18 minutes. Given that BEL charges 45 cents per kilowatt hour, calculate the cost of operating these appliances for the times stated. So let's start off first with the stereo. The power is 230 watts, but we need to convert that to kilowatts. Since kilo means 1,000, then we divide by 1,000 and get 0.23 kilowatts. The time stated is simply 3 hours. So energy is power multiplied by time. Substituting, we get 0.69 kilowatt hours. Next comes the electric griddle. The power is 1500 watts. Dividing by 1,000, we get 1.5 kilowatts. The time stated was 18 minutes. So converting that to hours, we divide by 60 and get 0.3 hours. Substituting once again, we now get 0.45 kilowatt hours. What will be the cost of both of these combined? Well, we multiply the 0.69 kilowatt hours multiplied by the 45 cents per kilowatt hour rate for the stereo, and we do the same thing similarly for the griddle. So the stereo alone will cost 31.05 cents. Rounded off, you could say 31 cents. And the griddle will cost 20.25 cents. Again, rounded off, just simply 20 cents. Exactly though, all of them together will be 51.3 cents. Now, mind you, in normal circumstances, you would round that down to 51 cents, but the electric company wouldn't do that. They'll round up in their favor.